First, we will go through the half adder code. So before that, we'll start with what is half adder and what are the equations we need to write, all these things. So this is the truth table. Okay. So this truth table will defines you what type of outputs we are getting and what type of inputs we are applying. Okay, so here x and y are the two inputs I'm considering. Okay, so 0 0 0 1 and 1 0, four combinations I'm giving. Based on the two inputs, four combinations I'm giving. Okay, based on that binary decimal values 0 1 2 3. Okay, so 0 plus 0 means sum is also 0, carry is also 0. 0 plus 1 means sum is 1, carry 0. Okay, 1 plus 0 means sum is 1, carry 0. And 1 plus 1 means sum 0, carry 1. Okay, why I am getting carry 1 means 1 plus 1. Okay, so that means 2. 2 how can we write means, so 1 0 we can write. In this sum is 0 and carry is 1. Okay, so this is my truth table. Based on this truth table, I am getting some boolean expression. So that boolean expression how I am writing here is, x some output I am getting at one position and two position. So then sum equal to that inputs how I am writing is x bar y plus x y bar. Okay, in this way I will write, right? This is the exclusive OR gate output. This is the logic diagram representation. Okay. Why this logic circuit is important means, if you are writing the Verilog code in a structural manner, okay, then structural manner you are writing means, then I need this logic diagram. Okay, so how I am writing this logic diagram means, see, some output is x XOR with y, that is the one output, and carry output I am getting at the third position. Then c equal to a, sorry, x into y I am getting the output. Okay, so this is the basic half adder circuit. Okay, so then logic diagram, how we are drawing the logic diagram, all these things. Then uh, we will go through the code, how we are executing the code in our playground. Just I want to show you the code. So same thing, we will go through the code. So this is my half address code. Okay, see, half adder design code. I told you that, so two inputs I am taking. Okay, A, B are the two inputs, and I am getting the two outputs, sum and carry. Actually, I need to mention the input type, either net type or rich type. Here I am not mentioned anything means, here it is taking like a wire type. Default is wire type. And then see, what is the that abstraction level I am following here. Here assign keyword is the data flow model. Okay. So directly I am assigning the sum output. What is the sum output? I got the equation from that A XOR B, or I am taking X and Y, X XOR with Y. Here A and B I am taking. That is the difference. Nothing will be difference here, right? This is my design code. Just two outputs, sum and carry. So those two are assigning by using assign keyword, because these are combinational circuits. That's why I will go through the continuous type of assignment. Okay. So this is my continuous assignment, because assign keyword we are using means that is combinational circuits and is also a continuous type of assignment. Okay, so this is my design module, module name, ports list, and then data flow modeling I'm applying, that is related to my functionality. After that, end module. So simple code. Okay. So now how to write the test bench? See, whatever the input ports list are there, all the things we need to represent here also. Okay, so I told you output is the in wire type we are utilizing internal world, and then external world we will write as a here both are wires we are using. Why we are using wires only? Because it is a continuous assignment combinational circuits. There is no need of memory. Okay, so there is no need of memory based, that is the reason I am not utilizing any rich type outputs here. Okay, so then wire is the, so and there is no need of wire rich type here, because wire is continuously driving the inputs. Whatever the input I am giving, that will continuously driving the output. Okay, so then my output is getting immediately. So that is the reason I am not representing the rich type of outputs here. If you use the sequential circuits, then we need a range type because we need to store the outputs values here. Okay, so then in the design model you will use the range model, and then design test bench side we will use the wire model. Okay, so that's why I'm default net type I'm considering, that is the wire type. Okay, so ports declaration completed. After that, we need to instantiate our DUT in test bench side, because this instantiation will tells you and my DUT is connected with the test bench, or test bench is connected with the DUT. Both are connected together. So this instantiation will tells you that your test bench is connected with the DUT and the DUT is connected with the test bench. Okay, the right side part is the design code and the left side part is the test bench code. Okay, see codes list I have mentioned. After that instantiation I need to write that. Okay, whatever the variables I am taking here, a, b, sum, carry. So same in same ports list also I am also considering in the test bench side, but few of the designers will consider, so a in, b in, sum out, carry out, in that different names they will consider. Anyway you can consider, no problem. So and then instantiation I am done with the name based instantiation. So name based instantiation we can connect anywhere, any ports, anytime, anywhere, so any position, no problem in that. If you follow the ordered based means, then we need to follow the whatever the order we are considering in the design style. Okay, same order we will consider in the test bin side. Okay, so then name based assignments I'm considering here. Then I will get the I'm instantiating. How I'm instantiating? Half adder is my module name, and UUT, that means user under test. Like DUT, how we are saying that design under test. Then user name is mentioned that UUT. Okay, user under test. Okay, whatever the design you are considering, that user is testing, that is the UUT name he is considered that. Okay, any name you can consider, suppose your name, so some Shashikant or Shankar or Priya, you can mention any name. Okay, you can also mention any name, that is the user defined name, because I want to know my DUT is connected with the test bench or not. So this is my DUT name, and then this is my username that is connected with my test bench. How I am connecting that? Here port list is there, A, B, some carry, then dot A of A. This dot A, first one defines the DUT signal, and inside brackets is represents the test bench signal. Okay, then my DUT is connected to the test bench. Okay, and then initial begin. This initial begin executes once in a time. Okay, inside the initial begin all are executed at t equal to 0 time only. Okay, This display, what is the purpose I am writing this display with? Just line segregating the inputs and outputs here. Okay, a b, a space b, and then some pole I have represent that. So this will segregate that inputs and then outputs. Okay, same will be appear at the output side. Just for looking purpose only I am writing this display statement. Okay. Then test case 1, that means idle case, a equal to 0, b equal to 0. This is my stimulus, and I'm displaying the outputs here, inputs and outputs. Dollar display a percentile b represents that a value, this percentile b represents that b value, and this percentile b is representing for some value, this percentile b represents for carry value. Okay, we will get the values by using binary values. So we will get the output and input values at the output side and the display side in the binary format, because percentile b represents that binary format. Okay, so then another test case, similarly another test case I'm considering here. Same output I'm getting, and then test case 3, test case 4. Just run this code and see that. See this dollar finish, we will call that at the end of our test cases. That means this dollar finish, what is the use of that? Means it will terminate my simulation. Okay, it will terminate my simulation, and then we will get the output like this. Just see. Huh. See, this is the display purpose. See, some table format I got that output, right? Whatever the truth table I have shown in this class, same output I got that, right? See, same truth table I got that output side. Okay, so then my half adder is working fine, right? So this will shows that my half adder is working fine. 0 0 I am giving, sum is also 0, carry is also 0. 0 1 I am giving, sum is 1, carry is also 0. 1 0 I am giving, sum is 1, carry is 0. 1 1 I am giving, sum 0, carry 1. Okay. So this is the basic code. Similarly, we will go through that some full ladder circuit by using two half adders. I want to design full ladder by using two half adders. How we will get? We will see that. See, this is my full ladder design code. Okay. So how we are designing full ladder? Three inputs we need to consider, right? And then how many outputs I am getting? Again two outputs, sum and carry. So then again I am not representing any wire type or ridge type. Defaultly it will take that wire type only. So A, B, C in sum and carry. Okay. So these are the local variables I am taking that. Okay, so all these are global variables and these are the local variables. Okay, so why I have considered these local variables means because I am designing the full adder circuit by using two half adders, right? Okay, how I can design that full adders by using two half adders? This is my half adder design. So this will be instantiated in my full adder circuit. Okay, just I am taking the full ladder inputs A, B, C in some carry. Okay, so then by using full ladders, by using two half adders, I am designing the full ladder. In the first half adder, same outputs we are getting, right? Sum and carry. Then dot A of A, dot B of B. This sum is connected to S1. Why it is connected to S1? And then this carry is connected to C1. This S1 and C1 is the internal wires. Okay. So internal wires I am considering that. Then that is the reason I am connected to S1 and C1. Okay. And then second half adder. Then this S1 is connected to next half adder sum output. Then sum comma, the original sum is connected to sum, and then this S1 is connected to as an input of A, okay, and then Cin is connected to input of B. Then I got that sum output. Okay, just I will draw this diagram and then assign C out equal to C1 or C2. That means carry 1 or carry 2. Okay, how we have designed this design, just I will show you the diagram. Then S1 C1, and then what are the things he is considered here? S1 C1 internal wires, S1 C1 C2. Okay. Okay, so full adder diagram how I am drawing by using two half adders. So this is my first half adder, like one exclusive OR gate I am considering. So this is my half adder. A, B are the two inputs. Then here I am getting some one is the internal wire. Okay, that is the local wire he considered that. And then I am also getting one output carry output, then A, B are connected together. Here I am getting the carry output C1. Okay, another input C in I am considering here. Okay, this is my C in, and another XOR gate I want to connect this. This S1 is connected as a input A. Okay, is considered right dot S1 of A. Okay, so this S1 is the internal wire and A is the actual input for this XOR gate. Okay, and then Cin is the another input. Okay, so that is the reason Cin is connected here. And then my sum output I am getting here, that is the original output. For the second half adder is connected dot sum of sum like this, right? So then sum is connected to sum, then full ladder circuit is happening properly here. Then this is the another carry. Okay, so this carry is connected to S1 here. Okay, and then C1 is Cin is already connected to this one, this is called C2. Okay, carry 2. Okay, because he considered S1 is the sum 1, C1 is the carry 1, C2 is the carry 2. Okay, and this C2 is connected to another OR gate. Okay, C2 plus, and C1 is also connected to this OR gate. Okay, then I got the carry out C out equal to, that carry out is the combination of C1 or with C2. Okay, that is the thing I have designed in my design style. Clear? Any doubt in this? So because of this reason only, I am considering the internal wire C1, S1 and C2. Okay. Now this design is completed. Then go for the test bin side. See, this is the full ladder design. Are you understood how I am connecting this one? A is connected to A, first order, first half adder, but sum output is connected to S1 and carry output is connected to C1. Okay, internal diagrams. Okay, internal wires. Again, this is the hierarchical design. I'm telling you, the previous one is the simple design and this is the hierarchical design. Why I'm telling the hierarchical design means outside another module is there. This module we are instantiating in the inside of the full ladder. Okay, so this will go through whenever it will trigger the A, B, C values. It will goes to half adder only. Okay, this values only we are getting it, we are triggering. Okay, so for this integrated one only I have driven the test bench. Okay, See, ABC values are reg I am considering, and then sum and carry is the wire. Okay. So then instantiation. How we are instantiating here? A, B, C in A is instantiated with A, B is instantiated with B, C is instantiated with C, and sum is instantiated with sum, carry is with carry. Okay, C out with carry, C out, carry with C out. And then this is also display purpose only. I am writing that. So separating the A, B, C, these three are inputs, and then sum and carry. Okay, outputs. For heading purpose, I am writing this display. And then, huh, yeah, this is the design code instantiation. So full ladder is the my original design code. Okay, module name, and then UUT is the user defined name. Okay, dot. Huh. In design code also we have instantiated, but half adder we are instantiated. Okay. This half adder instantiation is this module. Okay. This module I am instant because in our Verilog it is not allowing one module inside the another module, but those instantiation is allowed. Okay. We are designing the two half adders. Okay. Full adders by using two half adders. Okay, this half adder instantiation is needed, half adder 1 and then half adder 2. Again, this half adder is going to this half adder module only. Okay. Huh. Instantiation, this full adder instantiation I am done in the test bin side. Okay, this half adder instantiation I am not done in the test bin side. Once this full adder instantiated in my test bin side, whatever the ports lists are there, then it will trigger in this input. Once A, B, C values are triggered here, then A will be going to this half adder. Then this half adder will goes to this module. Okay, so this is the hierarchy. See, top is my test bench is my topmost module. Okay, in that my full ladder is instantiated. Then inside the this full ladder is going to my test design board. Inside the full ladder, what are the instantiations are there? Half adder instantiations are there. Then again it goes to the half adder. Then this half adder instantiation again points to half adder module, right? And the full ladder and the test bench. Inside my test bench, full ladder circuit is there. Okay, this full ladder circuit points that half adder. Then this half adder will works to together, and then I am getting the output at my test bench side. Okay, here three modules are there. One is top, that means test bench. Other one is full ladder and half adder. Okay, both are interconnected each other. Okay, clear. Then test bits. See, 000, 001, 010, 011, 100, 101, 110, triple one. All the test cases I have given. Okay. Which one? For loops we can't use. Here we can use the for loop in the test bin side. In the test bin side we can use the for loop. See, simple for loop you can write a equal to 0, b equal to 1, c equal to 0. So in this way a, b, c values we can mention that. And then in for loop for I equal to 0, I less than 8, I plus plus 1, and then I plus plus. Inside that you can write the concatenation operation a comma b comma c n equal to I. Then it will be considering all the values. Okay, so in that way also we can write. Then single for loop will entirely all these values will be printing, and instead of dollar display you can write the dollar monitor. Then dollar monitor will continuously monitoring the changing values. Okay, clear. So shall I run this code? Now you can see the output. So A, B, C in sum and carry. So 0, 0, 0, sum is 0, carry is 0. 0, 0, 1, sum 1, carry 0. 0, 1, 0, sum 1, carry 0. Okay. So 0, 1, 1, sum 0, carry 1. So this truth table, whatever we have explained, same will be appeared at the output side. So then we can say that your full ladder is working fine accordingly by using two half ladders. Okay. Okay. Then next one we will go through that binary to gray code, how to convert the binary to gray code, and then what is the signals we need to consider. You know already how to convert the binary to gray code, right? So just I want to brief that binary to gray code conversion. See, this is my binary. So bin I am considered here, and gray. So this is my gray code. So here bin 3, bin 2, bin 1, and bin 0 I am considering. Okay, bin 0. Okay. Similarly, I will consider some 1, 1, 0, 1 is my input as a binary input, and I am getting the gray code. This bin 3 is getting at the gray 3 as is. Okay. So gray 3 is that same output, whatever the input I am giving, same output I am getting at the gray code. Okay. So B3 will be getting at the G3 position. Okay. And then do the XOR operation between the B3, that means bin 3 and bin 2, binary value 3 and binary value 2. 1 XOR with 1 is 0. Okay. So then you are getting the output like gray 2. Okay. So this gray code, gray 3. Okay. So this output will be bin 3, and then uh, gray 2, how we are getting that, bin binary 3 pin XOR with binary second bit. Okay, binary third bit XOR with binary second bit. So that is the output we are getting at the gray second bit. Okay, similarly do the XOR operation between the binary 2 and binary bit 1, and I am getting the 1 output here. So, so 1 XOR with 0. So this is equal to not 1 1. Okay. So then that means how I am writing that 1 XOR with, see, 1 XOR with 0, I am getting 1. Okay. So this equal to is the writing in the downside. That is the reason I am writing here. Okay. So then I am getting the gray 1 bit position value. So how, what is the formula for this one? So gray 1 equal to binary second bit XOR with binary first bit. Okay. And then again do the XOR operation with that. 1 0 XOR with 1 is 1 I am getting, that is the gray 0th bit. Okay. So that means gray 0th bit, what is the output we are getting? binary 1 XOR with binary 0. Binary first bit XOR with binary 0th bit. Okay. So then same thing we will implement in the design code side. Okay. Just remember these equations: G3 equal to B3, G2 equal to B3 XOR with B2, and G1 equal to B2 XOR with B1, G0 equal to B1 XOR with B0. This will implement as a code. Okay, so design code. See, I am taking as an input bin and then output is gray. Okay, so gray third bit is equals to bin third bit. So both are as is, and then I am using the continuous assignment assign keyword. So this is data flow modeling. Okay, so gray 2, that means gray code second bit output how I am getting means binary third bit XOR with binary second bit. Okay, so then gray binary 2, sorry, gray code second bit I am getting the output side, and then gray code first bit how I am getting here binary 2 XOR with binary 1, binary second bit XOR with binary first bit, and then gray 0, that means binary 1 XOR with binary 0th bit. That is the simple design code. Then you can do gray to binary. Okay, so that is leaving to you as a assignment, like do the gray to binary code. Okay, binary to gray code I have done. Then gray to binary, how we can do the gray to binary? So previously we had done the input side only, but here output is also depends. This gray 3, sorry, G3, G2, G1, G0 is the inputs you will consider. B3, B2, B1, B0 is the outputs you need to get that. So this B3 is as is of the G3, but B2, that output is getting, how I am getting that B3 XOR with G2. Okay, then you will get the B2, sorry, that means B2 output. Okay, and then B1 output how I am getting means B2 XOR with G1. Okay, so then B1 I am getting that, and B0 how I am getting this G1 XOR with B, sorry, B1 XOR with G0. Okay, in this way we will get the output of B3, B2, B1, B0. Understood, right? Same thing. Here my module is there, and then module name, so test bench name. After that, inside the variables, what we need to represent here in my DUT, I am considering the default type net type. Okay, so net type only I am considering here. Then wire is the gray code, and reg is the binary value, because inputs I need to store in my test bench side, because I need to drive the stimulus. That is the reason I am storing the values in the register. Okay, this is my DUT instantiation. My design name is binary to gray code, and UUT is the user defined name. Two inputs I am instantiated here: bin bin of bin dot gray of gray. Same display purpose binary gray, and then we can use DUT also. No problem. You can name it as UUT or DUT, UDUT, or your name, anything. That is user defined name. Okay. So you only define the name. Okay. Then initial begin, I am giving the stimulus here. Okay. So bin 0, 1, 2, 3, 4, 5, up to 15 values I will give the stimulus. Then I am running the code. See, binary code and then gray code. See, 0 XOR with 0, 0. So first bit 0 is as usual. So see this example. So 0 1 1 0. 0 is as is. 0 XOR with 1, 1 I am getting here. 1 XOR with 1, 0 I am getting that. And then 1 XOR with 0, so 1 I am getting output side. Okay. This is a simple example for binary to gray code. Okay. Similarly, we can go through the other code. So I'm designing 4 by 1 marks by using 2 by 1 marks. Okay. So how we can design? So 2 by 1 marks we need to consider single select line. That single select line is common to first multiplexer and second multiplexer. See, this is the code. Here also we need to consider some internal wires. Okay, because so 2 by 1 marks we are using, right? So then how to draw the circuit diagram here? First I will explain the block diagram here. So this is my 2 by 1 marks. Okay. What is the output I am getting for 2 by 1 marks? Two, two inputs I need to give. One output I will get at a time. Every time I will get one output. See, this is the 2 by 1 marks I am taking. So how many inputs I am giving? So multiplexer means what is that? Multiple inputs we are giving. 2 power n number of inputs I am giving. One output I am getting. Okay. So n is that number of select lines here. Okay. So 2 by 1 marks means one select line is there, S is there, and then I naught I1 is the two inputs. If S equal to 0 I am giving, I am getting the output side is Y. Sorry, I naught. And then S equal to 1 I am giving, I1 is getting at the output side. Okay. So now I need to design that 4 by 1 marks by using 2 by 1 marks. Okay. See, not only 2, we will use 3 2 by 1 marks here. Okay, this is 2 by 1 marks. That is the inputs like I naught and I1 here, and then here select line is there. This is select line, and then another 2 by 1 marks, that is I2 and I3. So then four inputs I will be considered here. So based on this select line is 1 I am considering here. Okay, select line 1 means 0 you can give means, okay, so 1 this will be connected one thing. Okay, either upside one or lower side one. Okay, so based on this we will connect that outputs. Okay, so then huh, so this will be connected to upside, and then this is connected to downside. Okay, one is connected through some NOT gate. Okay, sorry. 2 by 1 marks, two select line, only one select line. Yeah, yeah. So this one select line. So this is the yes, no, select line 1. Okay, and then another 2 by 1 marks we will consider here. So this output y naught is the output, and this is the y1 is the output. Okay, y naught is connected to another input, and y1 is connected to another input. Here another select line 0 I will consider here. Okay, so then we will get the outputs like this. Okay, So this is my y output. Okay, in this way we need to connect that. So select line 0 and then select line 1. Okay, both two select lines are there, so that means select line 0, select line 1. Okay, 0 0 0 1 1 0 1 1, four conditions. And then outputs I need to get that I naught, I1, I2 and I3. Okay, if here if this is also 0, this is also 0 means, okay, I naught will be the output I am getting. Okay, so this is 0 and this is 1, then I1 is the output I am getting. Okay, so then I1 through y naught only I am getting the output. And then this is 1 and this is 0. Okay, so this 0 again, I2 is the output I am getting. Okay, and this is 1, both are ones, I3 is the output I am getting. Okay, so in this way we will design that 4 by 1 mux by using 2 by 1 mux. Okay, not 2 by 1 mux, 3 2 by 1 mux are needed here, because these two outputs are again connected to multiplexer. Okay, one time I am getting the this output y naught, and other time I will get the y1 output. Understood how I am designing that? Okay, so now you can see this the code, how the code is written. Okay, so this is my 2 by 1 marks. Okay, so in that I naught, I1 is the two inputs, and then select line is the one input, and then y is the output. So select line is also input only. Based on the select line only, we are getting the output which input we are selecting. Based on the select, so remote is the input only. Based on the input, which channel you want to see. So that is defines that output. Okay. So select line is the input only. So based on the select line, if 0, then false output I am getting, I naught I am getting. If it is 1, I1 I am getting here. Okay, again, same will be written here. So I naught, I1, I2, I3. So four inputs, and then S naught, S1 is the two select lines here. Okay, so then wire 1 and wire 2 internal wires. That means Y naught and Y1 is the two outputs, right? So those two outputs I am connecting this wire 1 and wire 2. Okay, W1 and W2. Then I am instantiating the mux 2 by 1 with those inputs, I naught with instantiated with I naught, I1 instantiated with I1, and then select is that instantiated with S naught, because S naught is 0 or 1. Okay, based on that, these two select lines will be considered. And then the other select line is connected to, so mux 2 is also connected to S naught only, because mux 1 and mux 2 is connected to common select line S naught only. Okay, and then mux 3 is connected to select line 1. Okay, so this select line 1, based on this, so this will be valid. Okay, so why I am taking this select line 1 and this is the select line 0, because S naught and S1, S naught is 0 0, so one time it is S1 is 0 is maintaining, but S naught is varying either 0 or 1. If 0 is giving, I naught is coming, 1 is giving, I1 is coming. Again, this one also. Okay, for the S1, the second mux will be operating. S1 two times 1 we are maintaining. Then S naught is that 0 one time and 1 time. 0 will taking means I2 is getting the output, and 1 is giving means I3 is the output I am getting. Clear? This is the design code. Okay, so end module. See, this is the hierarchical design again. Okay, because this 2 by 1 marks I am instantiating in 4 by 1 marks. Okay, same thing. Inputs I am mentioning I naught, I1, I2, I3. and then select lines S0 and S1. See, display purpose S1 and S0. Then you can see I0, I1, I2, I3, and then output Y. So which output I am getting here? So I am passing the stimulus here. So 0 0, S1 is 0, S0 is 0. Then what is the output I am getting? Okay, see, here I0 or I1, which one is getting output we can see here. See, see, 0 0 I am giving. So S0 is 0, then I0 is the output. I0 output is what? 0, right? Say, then output is 0, I got that. And again 0 1, 0 1 means, so again I1 is the output. What is the I1 input here? 1. Then output I am getting 1 here. Again 1 I am giving. 1 means I2 I3 will be getting the output side. If you are giving 0 means I2 is the output. Okay, I2 output is 0. Okay, and 1 1 means I3 is the output. Okay, I3 is the 1, I am getting the 1 output. Clear? So this is the 4 by 1 marks design by using 2 by 1 marks. Okay. Similarly, we can also design the demarks. 1 by 4 demarks by using 2 by 1 demarks. See, 1 by 4 demarks by using 1 by 2 demarks. Same thing, same circuit diagram. So, but demarks it would be different, right? See, this is the demultiplexer. This is my 1 by 2 demultiplexer. That means single input. That is the reason I am telling you we need to learn digitals. Okay, digital basics is needed. Based on this digital basics only, they are designing the design code, right? See, uh, this is my 1 by 2 demultiplexer. That means single input I am giving, two outputs I am getting. Based on the select line, I am getting the C. Enable pin is that just for operating purpose. If the enable pin is 0, okay, so then S naught and Y1 and Y naught are unknown values. Okay, so Y naught and Y1 are zeros here. Okay, so and then S is unknown value. That means 0 or 1 you are selecting, then nothing will be getting at the output side when enable is equals to 0. Whenever enable equal to 1, okay, so depends upon the select line is 0, I am giving the input 0, okay, so then out, sorry, select line is 0 means the A will be getting at the output side at the Y naught side. Okay, so Y naught channel is selecting. If select line is 1, then output is at the Y1 side. This A will be getting at the Y1 side, like a broadcasting purpose radio. So single channel, we are producing that 93.5 red FM is there. Okay, so this FM is a single channel but multiple users are there. Okay, so or another example, you can take any example like broadcasting, right? So I'm the only one broadcaster and you are the three persons listening at a time. Okay, that is also like a demultiplexer. Okay, single transmitter, multiple receivers. Okay, see now, uh, which one? No problem. You can write
But the total is correct.
this is y naught and this is y1. You can write anywhere. No problem.
Zero is
Ah,
given, output will be
output will be getting.
y
See,
y
this is my 2 by 1 marks. Sorry, 1 by 2 d marks. This is 1 by 2 d marks. Here, one select line, one input I am giving. Okay, so this inputs will be common to these two values. Okay, a is getting here, and then I am getting the two outputs. This is y naught and y1, and here also two outputs I am getting y2 and y3. Okay, so then one input, four outputs I am getting by using two by one, sorry, two 1 by 2 demultiplexers. Okay, so in this way we will get the output equations. Okay, let's see the code. Select line will be two needed, right? Uh, No, I think select lines also two needed. Then another demultiplexer we need to write. We need to draw another demultiplexer. So that means these two outputs are connected to another what it called. Sorry. See how I am connecting here. So it's little bit difference is there. Just give me 1 minute. So here two inputs are connected to same, right? Just you need to draw the another 2 by 1 marks, sorry, 1 by 2 d marks here friend. Okay, here two outputs I am getting, single input I am giving a, and another select line. This is the another select line. This is one select line. This select line is common. So this is s naught and this is s1. Okay, so here two outputs I am getting. One output is connected to this one and another output is connected to this one. Okay, so then so three 1 by 2 demultiplexers are needed to design a one 1 by 4 demux. Okay, I forgot some formula is there. So how many demultiplexers are needed, and then how many are required to design for suppose 8 by 1 1 by 8 demultiplexer you want to design by using 4 by 1 by 4 1 by 4 demultiplexer. Then again 3 is required. So but how it is required means some little formula is there. I forgot that. I will remember again. So then I will say in the next class. Okay. See, that is the reason we are writing D 1 by 4 1 by 2 demultiplexers. See, D2, D3 and D1. Okay. S1 is connected to D1, first demultiplexer. And then S naught is connected to two demultiplexers, D2 and then D3. Okay, and then internal wires we need, right? Y1 and then Y naught is that. Here he is considered W0 and W1. That is the internal wires he considered. Okay, Y naught is connected to W0, Y1 is connected to W1. Okay, similarly, y naught is connected to y naught and y1 is connected to y1. Okay, y naught is connected to y2, and then because y naught y1 is the first demultiplexer inputs. Okay, and then sorry outputs, right? Y naught y1, and then second demultiplexer outputs is y2 and y3. So again, those two are also connected to y naught and y1 because these two are the outputs from the previous demultiplexer, right? Y0 and Y1 are the previous demultiplexer outputs that should be connected to next two demultiplexers. Okay, so remember, imagine that diagram in your mind, then code it. understand the code. Okay. See, this is the 2 by 1 mux. Y0 and Y1 is the two outputs I am getting. Okay. So these two outputs are connected to internal demultiplexers. Okay. Same thing I have written here. Okay. So taking the inputs S0 and S1 range, and wires are the Y0 and Y1, Y2, Y3, and then D is what? So internal wire. Okay. Some S0, S1, and D is the input, right? Another input we are considering for the demultiplexer. First input of the demultiplexer. Okay, so that is the D. And we are connecting to all the inputs. After that, giving the stimulus here, D, S1 and S0, Y3, Y2 and Y1. See, you can see it like a decoder. Like two inputs I am giving, four outputs I am getting. Y3, Y2, Y1, Y0. So if you run the code, then we will get the decoder type of output. So 4 by 1 demultiplexer acts as a 2 by 4 decoder. Two inputs I am giving, four outputs. So these two inputs are select lines 0, 0, 0, 1, 1, 0, 1, 1. So during 0, 0, what are the inputs I am having that will be appear at the output side. See, this S1 is 0. Okay, so S1 S0 is 0 means Y0 is the output I am getting. Okay, and then S1 is still 0. So this S1 will decides that first demultiplexer we need to take the output, or second demultiplexer we need to take the output. Okay, S0 0 means first demultiplexer only operating condition. S1 is 1 means second demultiplexer is in operations. Okay, clear? Okay, so then 1 is giving here, S1 is 1, and then 0, Y2 is the output I am getting, and then S1 is 1 and S0 is 1, then Y3 is the output I am getting. See, this is like a decoder, two inputs 0 0 Y0, 0 1 Y1, 1 0 Y2, 1 1 Y3. Yeah. So next LFSR. What is that LFSR? Linear feedback shift register. Okay, so linear feedback shift register, what is that working, how it is doing? See, linear feedback shift registers is used to generate pseudo random numbers or pseudo random patterns. Like in my during the test bench side, I want to generate different values every time. That is the pseudo random pattern generation I want to generate. Okay, so this pseudo random pattern, how it is generated means, suppose 4 bits I am considering here. Okay, parity generation purpose, this linear feedback shift registers are used, and other purposes this linear feedback shift registers are used. Some error detection purpose we are using this one. Okay, see, my system got old, so it's showing that I am olded, so I am aged person. So we need some time. You are switching from from internet to PPT, PPT to internet. So you are switching fast, but I'm not that much fast. It's fine. See, this is my 4-bit shift register. Okay, so linear feedback shift register LFSR. Okay, so here every time we are getting different patterns. Okay, every time I want to get different patterns. Suppose I'm feeded 1 0 0 1 0. Okay, so how it is taking means 0 0 1 0 bit only is considering that, and then this first some 2 down to 0 bits are common here. Okay, then third bit, that is the because 4 bits I am considering. Okay, so 3 down to 0, this is the 4-bit representation, and in this 2 down to 0 is common, and then we are taking first, and then third bit, that is feedback bit. Okay, so that feedback bit, how we are doing means, so this first bit, and then uh, this last bit we are doing the exclusive or operation. Why exclusive or operation means, exclusive or operation only giving the 1-bit change. Okay, so every time 1-bit change we are getting, that's why some random patterns are generating. Okay, so first we are taking this 2 down to 0. After that, feedback will be assigned at the first position. Then every time random patterns will be generating. Okay, let's see. So this is my feeded bits. Okay, 0 0 1 0. Okay, so again this 0010 we are writing. Okay, so then what is the value we are getting? The pattern is, so exclusive or operation between 0 XOR with 0 only we are getting. This is my feedback. Okay, so first I need to write the 2 down to 0 bits. This means 0 1 0 is the my feed 2 down to 0 bits. After that feedback I need to write that. Then so this bit will be randomly generated, right? See, whatever the pattern I am giving, 0 1 0 0 0 1 0 I am giving. What is the output you are getting? 0 1 0 0. Different pattern. Suppose you are feeding another pattern like 1 1 0 1. So 4 bits position. Every time it will produce that. So some self-checking purpose we are using that. So internal errors we are getting. We need to correct that. So for self-checking purpose, these LFSRs will be used, and scrambling purpose we are using. Okay, you know built-in self-test, BIST. Okay, in VLSI we will get that built-in self-test. I think built-in self-test, it will be correcting the bits automatically. At that time also this LFSR will be used. Linear feedback shift registers. I think you know any built-in self-test. Okay, no problem. Don't uh, strain your brain. Okay, so these two bits will be XOR together. 1 and 1 XOR with what is the output? 0. Okay, 2 down to 0 means 1 0 1 and 0. Then random pattern, every time random pattern will be generating. Okay, let's see, like a shift register, like 1 bit. See, 1 1 0 1 we are giving as an input. Okay, do one left shift operation for this. What is the output? This 1 is going out, 1 0 1. This is coming here, then 0 will be placing here. Then same thing will be operating. It's like a left shift operation, but every time random patterns will be generating. Okay, so now we can see the code. Understood, right? How it is happening. Okay. See, this is the code. I'm taking the clock and reset. So LFSR 4 bits I have considered. That is my output. Okay. Sometimes they will ask you some registered output. They will ask you. Okay. This LFSR is also acting like a registered output. Without giving any input, we only feeding the input, and then that only producing the output. Different outputs we are producing that. Okay, clock reset, and then some LFSR we are giving, and then wire is the feedback internal output. Okay, so then assign feedback equal to LFSR of third bit, and then first bit we are doing the XOR operation. And then what is the condition? Reset condition. During the reset condition we need to feed some value, we are saving some value. Okay, after releasing the reset, it is taking the values like this: LFSR 2 down to 0 comma feedback. Okay, so 2 down to 0 means, so what are the 4 bit you are counting? 3 2 1 0. So these 3 bits will be appended first, after that feedback will be appended. Okay, concatenating, these two are concatenating, combining together. Here, this is the operation, pseudo random pattern generation. Okay, same thing I have considered here. And then, so clock generation, how I am generating the clock? Always initializing the clock, initial clock equal to 0, this is the initialization. And then clock equal to negation of clock every 5 time units, simulation time units, my clock will be toggled. So that means 1 for 5 time simulation time units, again 0, and then 1. In this way my clock will be produced. Okay, so then just nothing will be giving, right? Just I want to monitor that LFSR bits. Okay, so time slash t. This slash t will defines you tab. Okay, spaces, lexical conventions I have explained, right? And then dollar time, every time unit it will be representing that. So this dollar monitor will be representing this my time and LFSR. Okay, just run the code. How many bits we are considering? 4 bits, right? So how many combinations we are getting? 16 combinations. After 16 combinations it will be ending the simulation. Okay, see. Okay, so 0 at 0 at initiation time, 0 0 1 I have feed it. Okay, so just do one right shift left shift operation, 0 will be going out. Okay, so what is the output we are getting? 0 0 1 is the 1, and then doing the XOR operation 0 and 1, then first bit will be 1 here. So random pattern is generated here. Same thing you can check every bit. Okay, previous is the input, and then next is the output. Okay, so this is the linear feedback shift register. Okay, I'm stopping here now. Okay, so then tomorrow we will see some pattern detections, and what it called pattern detections, and then FIFO. Some, see, you can see the